So we're now transitioning to the panel portion of the discussion. So we have people monitoring a chat on Zoom. So if you're joining us virtually, please put your questions in the chat and we'll make sure we'll get to them. If you have questions here, I believe that you can speak into the mic closest to you and ask your question directly of the panel. So if you have a question, please raise your hand and wait to be called on, and then you'll get a chance to answer your question. I think quickly it'd be helpful to everyone to say 5 seconds about who you are and the type of research you do before we get started, just to orient. You want to do that, Miguel? Everyone other than Miguel and Jamie, maybe?
I'm here at the Public Health School. I'm a professor at the Public Health School, and I research on methods for causal inference.
I'm Sara Lodi. I'm an assistant professor in biostatistics, and my work mainly focuses on use of causal inference methods in clinical trial and observational studies using big data in the area of infectious diseases substance use disorder.
I'm Issa Dahabreh. I'm faculty here at the school. I guess my relevance here is do some work about recalibrating a trial to a target population, and so the idea maybe you could do this to facilitate the kinds of comparisons Jamie was talking about.
Can I do exactly the same things as
Okay, so we're here to answer the question about how do we know if we're right, but the question that I would like to start and ask the panel is, can someone give me a clear definition of what it means to be right? So before we ask how do we know we're right, what does it mean to be right in the first place? Miguel, you look eager to answer, go for it.
So after we define what is the relation of interest and what is the set of strategies or treatment strategies or set of interventions that we are interested in, what is the outcome of interest? And those things are well defined or as well defined as we can for our purposes. Then we can think of what is the hypothetical experiment that will compare those strategies in that population to see what the outcomes are on each of the strategies. And that contrast is what I think we want to do. But
No.
More succinctly, we don't later want the reputational damage of somebody doing the randomized trial and found out that people have been being hurt by our previous advice.
Sarah, you say anything to add to that?
Yeah, so I think that we will never know if we are right or not. All we can do is we can try to use the method that we have as best as we can. And then very, very importantly is that we understand the data that we use. Otherwise, we cannot achieve, I think, any good causal inference estimation. And also another important thing is try to put our results into context with other observational study and clinical trials. So what I was saying is that we don't know, we will never know if we are right or not. Okay, now you can even, okay. And then we should always be critical and of the method that we use, and always try to put our results, our finding into context with other observational study and clinical trials.
Okay, you say anything to add to that? Or I think we're good. So I do want to just ask a clarifying question then, because in the opening talk from Miguel, and anytime you take a causal inference, there's this statement. So it sounds like the definition of right is contrast with the target trial of interest. We design the target trial, and then the right answer is recovering what you would have gotten if you could have done that randomized control trial. It seems to me one of the big opportunities for causal inference from observational data are scenarios when that trial is impossible or unethical. And so are we still thinking that the definition of right is if we could do the randomized control trial even in these situations, even in situations where it might, like an RCT is not maybe the most natural way to pose the problem. Is that still the correct definition of right?
Okay. Yeah, so I think that we need to realize that that the target trial is just a device to make sure we know we're asking a question that makes sense. Everything that we have set out in the target trial, except for the most complex things that Jamie and others have developed in the last few decades, is the same as saying, just use sound study design. But use sound study design sounds very abstract to many people. You tell them, you ask them the question, what is your target? Then they start to focus on some of these important aspects of sound study design. The whole point is to make a well-defined counterfactual contrast. But if you ask a doctor, okay, what is your counterfactual contrast? It doesn't work as well as you ask the doctor, what is the hypothetical randomized trial that you would like to design? It's exactly the same thing. So, and for questions for which you cannot have a randomized trial, like for example, the question that Jose was describing at the end of today's session, you can still think of a hypothetical counterfactual contrast that is really what we are after here, I think. And the problem with many of these analyses we're asking for, how do we know what is the thing that we want to the right? The problem is that many analyses of observational data have not gone through this exercise. They just go to the data and fit a document with something. And then it's impossible to know how to interpret that. It's not even wrong, it's just what are you trying to do?
Yeah, so I don't know. Yeah. So, I mean, I completely agree with the issues. Oh, you want to speak? It has been a while since I spoke with other people. Okay. So I completely agree on the issues of meaning. You have to know what you're measuring, the variates, the treatment, the outcomes. That makes sense. Completely agree on the device of the trial. But I want to suggest that and you can see, Andy, I think slowly, so I will answer the first question.
Okay.
But I think it's related. I want to suggest that maybe the idea that we have a causal contrast and we can write it down and estimate it not once, but as Jamie was saying, twice, with a trial and an observational study, I think many times proves challenging. And so I think it's a useful aspiration. And I mean, it's a kind of weird because Jamie, Miguel and I worked on a paper that became so artificial just to do all the details in that case. And then so I think humbly, I submit that sometimes getting it right will mean weaker things than estimating the exact causal contrast in two data sets. And so, you know, I want to say I won't name names, but there's people who routinely collect the data and they produce numbers. And those numbers are not created using methods that under reasonable assumptions could recover the same causal quantity. In my opinion, imagine that is the case for some place in the world. So someone is running observational studies, and then they're comparing them with the trials of similar treatments and similar outcomes. And they get numbers, and these numbers mean something different than the ones in the observational analysis. And they put them in a scatter plot. If the scatter plot showed good agreement, I think Miguel's criterion would fail, meaning you are not estimating the same causal quantity because just it's numerical agreement you're achieving. But I feel that would also be useful. So I have taken the position that less explicitly causal, if you will, approaches can be useful because you're just getting a predictive model for what the trial would have found, even though the actions you undertook by no way guarantee that really a causal quantity is even estimated. Maybe what you're getting is some weird associational quantity that just happens to be in numerical agreement under some scale transformation with the trial. I don't know what's your thought.
Yeah, I just wanted to add something to just the point that you just raised. So I think that the target trial approach is good because it makes us think about the question. And sometimes, instead, like people rush to the analysis. Let's say, I want to, like compare these people and this group using Cox model. So why do you want to do that? Is that we are talking about method, we are not talking about questions. So let's go back and try to see what is the question, what is the population. And actually the target trial is a tool, approach is a tool that really helps the communication between, like epidemiology, statistician, computer scientists, clinicians, because we all speak the same language, because we all understand how to clinical trial and clinical trial design. So like you really take away the focus, and then the methods, once we have defined this, I think that the method flow, so like then, like the choice of the method, and then we can have several sensitivity analysis, do the analysis, the method in different ways, but we start from the question and then we adapt the rest.
Anything to add, Jamie?
What?
Anything to add?
No.
Okay, so I obviously could ask this panel question all day. I'd like to stop and see if there are any questions here from the audience. We have a couple on Zoom, but would anyone at this point like to ask a question of the panel from the audience? Okay, you can continue. Okay, we have a question here.
Yeah, I was wondering if we never know, as Dr. Lodi said, whether we are right or not. Does it make sense to compare trial results numerically with observational studies? Because we never know, it could be a chance that we get the same result, it could be emulation differences, different populations, it could be different measurement error, it could go all kinds of directions. And in many papers, you do compare the trial results with the observational estimates.
Yes.
So does it make sense? And then, that's my first question. Let's start.
Can I take those? I can start briefly. So I think, yes, so that is actually great when we have, like we've been talking today, Jamie and Miguel have been talking about benchmark trials. So like an existing trial that exists, we have the protocol, we understand it, and we have results. So then we can then design an observational study to mimic this existing trial as much as we can. And then let's say that we have a causal effect estimates that are in the same direction and same amount of magnitude. So that makes us more, it is reassuring. Of course, we will never know, but it is reassuring that we might have been able actually to account for the major confounders.
I think the thing is to remember what I was saying is that the research part, you can't, just the way you can't talk about an individual person, you can't tell about an individual study if that's what you mean, but the whole point is to get a lot of studies to do these kind of meta regressions to see what percent of them agree between the observational and the trial. So based on characteristics of the observational study. That's a generalization we're trying to make. What is reliable? Not that we're right in every case, but that if you do that over and over, hopefully, crazy chance things don't happen every time. That's what we mean by looking for systematic things in like a meta regression, what things predict whether they'll be agreed in a given study.
As a follow-up to those two things, when we're talking about benchmarking observational analysis with existing randomized trials, there are a lot of things that are for starters, we had to make sure that the distribution of baseline covariance is the same involved, and both Issa and Sara have been working on that. So we need to re-weight people in one or the other to be sure they're seeing. That is assuming that we can compare the same treatments involved and the same outcomes involved. But then we will have also the issue that everything that is done in an experimental setting may not be replicable in the real world. So if a trial has the placebo control, we are not going to if the trial has blinded for the treatment, we cannot do that. So it is important to set the expectations right. That what we can do with observational data is emulate certain types of randomized trials. No blinding, with no placebo. There are many actual trials that are like that, because when we want to know what works in the real world in a given healthcare system, we don't lie and we don't use placebo. So that is the type of trials that we want. But even after taking that into account, in the trial, there may be some enforcement of adherence, or maybe some tight monitoring of the people. That may not happen also in the real world. So, because what is published from the trials is typically an intention to treat effect. That in itself is not comparable necessarily what you get from an observational analysis, where you can mimic the same type of intention to treat effect, because there is no physical assignment to treatment. So that means that any serious comparison, we're serious about really what's going on. We don't only need to analyze the observational data. We typically will have to reanalyze the randomized trial data to estimate the same type of parameter that we would get in an observational study, something like a per protocol effect. And so that is another level of complexity that is usually bypassed that we need to. And Sara may talk about her experience doing this type of things.
Okay. Anything else from the panel? Sarah?
Can I add just to follow up with this? So I think that an important thing something that would be great is also for clinical trials to be more pragmatic in order, to be able to have, to be able to use these benchmarks, so to use, the results, the information that we have from an existing clinical trial. It would be good if clinical trials could be designed whenever we can as to have pragmatic aspects, including, for instance, a definition of an outcome. It doesn't have to be the primary outcome, at least include an outcome that is similar to, that is going to be similar to what we're going to find if we use claims data or electronic health records, for instance. So I think there should be also some thinking from our colleagues, or also I also do that, or statistician and epidemiologists who design clinical trials.
So I'd like to follow up with a question from chat that dovetails into that. So there's a lot of questions on the discrepancy between RCTs and observational data analysis. And one of the viewers had a question about, obviously we can never be 100% sure in an observational data analysis that we don't have residual confounding. So maybe Sarah, maybe you could talk to methods to understand the impact of residual confounding and how you might assess that when doing one of these studies.
So we are talking about, I guess the question is about, again, when we have a benchmark clinical trial. So the way to proceed is actually is to design the observational study using this benchmark trial as the target trial. So having the observational study to be designed to really follow as much as possible all, the characteristics of the clinical trial of interest. Then, at that point, after we have done that, our observational study might still be prone to a measure confounding. So what we could do at that point is to conduct some sensitivity analysis to try to determine, to try to understand if there is still some a measure confounding there, and obviously this is research specific, but there are tools that we could use a sensitivity analysis for that. Anything else you want to add?
It sounds to me, every time. Okay. It sounds to me we're kind of talking about two slightly qualitatively different problems. One is I have a beautiful benchmark and I have the data and I can reanalyze and I can harmonize things and I have a beautiful observational study and I can do that. And that's great. And I think it's closest to what we can do very carefully,
Yeah.
theoretically,
might
justifying
not
every
work.
step.
Mind
And
work,
it may
yeah.
still not work because of some unmeasured variable.
Yeah.
Completely agree.
Or some aspect of that is not possible to harmonize, yes.
But I used to be in the meta-regression business a few years ago. And I think the philosophy of the meta-regression that Amy outlined is more about some kind of response surfaces methodology, where whether these things that Miguel and Sara primarily mentioned are predictors. So were you able to get the contrast defined the same way? Did you have the same variant? Did you use an I'd go as far as say, we're taking a bet in the causal lab that if you take an explicit causal framework, you are more likely to get agreement. But there is people who will, in writing, say, I don't have access to the trial data, so I only have intention to treat, but adherence in the trial is usually very high. And then they'll say, so I will do a BAD, not adjusted for censoring, artificial censoring. I'll do a bad analysis of the observational data per protocol, because that gives me numerically the same answers. And so these people will be placing, I think, a different bet. They would say, we can predict what the trials will say without having that nice alignment. And I think we should, be interested in a game where we compete with a set of philosophies and attitudes, and we see who wins. I think the machine learning people like this sort of competition.
Right. Machine learning loves a good leaderboard, you're correct. So.
In line with it, if you do your best in an observational study and disagrees with the randomized trial, people are, there are going to be lots of reasons, like, and the disagreement between the randomized trial of post-menopausal hormones for heart disease and the observational studies. The observational studies, found a big beneficial effect. The randomized trial didn't, but there were, lots of differences in age and who chose to be in it and who was, these people were assigned to estrogens rather than hormones rather than taking them because they were symptomatic and so forth. So there were, lots of people who said the trial did not contradict, just because the numbers were different, they weren't contradictory. And there were suggestions to do other trials that were more like going the other way, or like on the people and on the data generated, the circumstances that the observational studies are actually analyzing. So everybody has, stake, position in the game. No one goes, says, oh, I disagree. The trial was right, I've always been wrong. There's usually a lot of reasons you could say that the trial wasn't relevant to the question, to the analysis they were doing. So it's not cut and dry. This is all fought out in the court of public opinion.
If we can step back for a second here about why we're even talking about this. If we see, there are things when we try to make causal inferences from observational data, there are things that are under our control, things that are not under our control. Under our control is how we choose the eligibility criteria, how we choose the treatment strategies, the outcomes. All these things, given what is in the data, we can use it in the exactly same way that it would be used in certain types of randomized trials, without blinding, without placebo, with measurement of the outcome based on medical records. There are trials like that. Those are the trials that we are talking about that we can try to emulate with observational data, not the phase 3 double-blind placebo control trial. That's not what we can do. So after we have taken care of everything that is under our control, what is left is confounding and measurement error. So the thing is, can we eliminate all these other potential biases that plague the literature? that are everywhere in the literature. And how can we get rid of those self-inflicted biases and be left with confounding? That is really what we are trying to do here. And that's what target trial emulation helps. So now it's really confounding what is left. And then we can worry about that. But then I'm going to say something that may be surprising to some people in the audience. It's actually very hard for us, at least, to find examples of observational studies that gave a completely wrong answer compared with randomized trials. After you analyze the data in a causally explicit way, assuming that you have some confounding measure. Of course, we are trying to emulate the trial of anti-retroviral therapy in the 2000s, and you haven't measured CD4 cell count. No, that is something that we should even try. But in cases where we have a reasonable measurement of confounders and we mimic an actual trial in a causally explicit way, we have not been able to find many examples where observational studies have gotten. And that, I think that is important. That's an empirical thing. And I'm saying this because I am hoping to see the chat full with examples of where this has been the case. This is the question that Jamie has asked during his talk. Do we have many of those examples? Because if we can convince ourselves as a discipline that when we do everything right and we adjust for confounding using the right methods, it's not very likely to get it wrong, then we'll have more confidence in the observational studies when we don't have trials. And we can use that to design trials to rule out some treatments that clearly don't work or that they have a lot of problems. We have seen examples today of some treatments that show some promise, that based on everything that we can do, they seem to lower the risk of severe COVID-19. They're not being studied in trials. And they're not being studied in trials, and people don't take it very seriously. This is because they are observational studies only. But when someone decides that an observational study is not, after mimicking the trial in the best possible way, it's not something that you can trust, then you must have some mental causal model of why you think that observational study is not reliable. And it will be very important to make that explicit. You cannot say, I don't believe this observational estimate because it is observational. No, this is science. You have to tell us why you don't believe that it is valid. Which confounders we are not adjusting for? Which part of the design are not correct? And that's what the target trial emulation thing is trying to help with. It's trying to rule out a lot of possible things, and so that we are left with a few possibilities and we can focus our scientific inquiry into that.
Just to follow up on that with a question from chat. So obviously that in itself sounds like a gargantuan task, but is there a use for these kinds of methods or this framework beyond target trial emulation? So the question is, are there lots of other non-trial analyses that suffer from the same sort of asking the wrong question kinds of problems? Is this type of framework more generally useful in observational data analysis, or is it just for simulating a hypothetical target trial?
I think I can start. I think that this is, in general, like what the target trial does, like try to think big. So let's try to think what would have been the ideal trial that we would have liked to design if we could. So I think that this way of, and then little by little, like you have to be pragmatic, and especially in the emulation with observational data. And I think this is an approach to design other studies that are not necessarily only for comparative effectiveness, but like, for instance, like when we think about estimate the prevalence of hepatitis C, for instance, in a population, you can try to think what would have done in a prospective study if I had a limited amount of resources. What would I do? And then, given that I don't have a limited amount of resources, what am I going to do? So, yeah.
So, yes, whatever. Yes. Okay. Let me see if I remember the steps. It is an interesting philosophical thing. My philosophical credentials are terrible, except that I'm Greek. And so we used to excel at the activity in the distant past. And so one thing in philosophy, I think, is that similarity is the promiscuous concept, because you can find two things and you can always find dimensions, because there is so many dimensions that the things are similar. And so I remember reading a book, I think by Bell, B-E-L-L, and they had a discussion. It's basic biostat ideas, and they had a discussion, and they said an observational study of treatment is like a survey. And so they made the idea, they had the idea that the ideal of some aspect that they were discussing was a survey sampling design instead of a randomized design. But I do think, with the limitations of similarity in mind, the idea of ideal studies to answer a research question is actually quite general. And so one could argue that if I want to estimate the prevalence, the ideal study is some kind of survey procedure, which, we have, like for randomization, smarter people than me have worked out the details for decades. And so it's an interesting thing, because you can do it in the design of the study, like Miguel and Jamie have spearheaded for target trials, but you can also do it, I think, in the assessment of existing studies. So you can judge a prevalence study against an ideal survey, and you can judge an observational study. I think, again, that Miguel has a contribution in the Cochrane reviews, where now observational studies are generally assessed against an ideal trial. So it's a pretty general idea, I think. It's very interesting.
Thanks. So I'm going to hop back to the end. So David has a question.
Hi. I was wondering about your thoughts on creating very large DAGs, and if you think that there is practical relevance to creating DAGs with many variables on them, and how to go about creating such large graphs. Do you think that there are issues associated with creating causal models that have more than, say, a dozen or 2 dozen variables, and how this kind of goes to the high-dimensional settings?
Jim, you haven't said anything in a while.
Before I answer that, which I don't have the answer to, but I will say I'm not as sanguine as Miguel about the success of all these methods. And I do think the issue of an observational study is, someone thinks it's wrong, they have to tell you why, is somewhat problematic, because in the old days, before people knew, a lot of time, like the old days when people would get terrible answers with observational studies because they weren't doing the analysis right. And then you say, well, what could be wrong? Name something that could be wrong. Well, those people couldn't name anything, because the people you are asking today, the things also didn't understand what was wrong with the analysis. And so therefore, you could say, well, it has to be right. You don't have any reason against it. I mean, I think the fact that you view observational studies as guilty till proven innocent is a good stance. Where the dividing lines are, I mean, maybe how skeptical you are, but they're, So that's this other question. Well, that's an interesting, I think, I always thought I could make big tags for like, what's going on a soccer field, or, where I actually understand the physical things going on. Once you start, chronic disease, we don't really understand how anything's happening. I mean, we know a lot more than we used to because of basic science and other things. And so much we don't understand about people. I don't put much stock in So something to rely on. Yeah. Do you? What do you think?
I don't know. I don't know. I'm thinking about it. I don't know yet. I'm just thinking about this issue with, with so much data now, and we have potentially so many covariates, but assigning causal structure to it is very challenging. And I'm just thinking about that problem.
And let me maybe reframe it a little bit. So a question that I think about a lot is there an opportunity for scale in causal inference? So coming from the machine learning side of things, the primary ingredient for success has been to reduce a problem to a problem of scale. And if you can get a large data set and fast computers, magic happens. So is there a large general purpose DAG that could help causal inference? Is it a sample size issue? What does causal inference look like at scale?
I think that's a fundamental question. So the main reason why machine learning, as we know it now, cannot automate causal inference in a concrete way is because of the lack of causal knowledge, or subject matter knowledge in the algorithms. In the sense that any human expert who looks at the data set and say, oh, you're trying to estimate the effect of statins on heart disease. You don't have LDL cholesterol in this database. Therefore, you can't. You shouldn't even try. But an algorithm doesn't know that. If you blindly say this, I have data on 100 million people, 5,000 features, tell me. And we'll try to estimate something that for any human expert would be obviously wrong. So that I think that is the part where once we're able to make computers have these causal models that are at least as good or as bad as human models, then they will be equal or better than humans doing this. And that's where causal lags might come into it. Maybe that is a tool that we will be using. I don't think we are close to have an all-purpose causal lag for all human knowledge of health that we can feed to an algorithm, but maybe more localized questions. That's something that is feasible. We now in practice use causal lags as guides. So if you think using causal graphs, then you know the type of variables that you will need for your so the type of variables that you have to worry about. You have to worry about compounds. So you can think about, okay, what are variables that in a causal structure, even if I don't know exactly where they are, but they will be in this random path between the treatment of interest and the outcome of interest, or will be highly correlated with those variables. So we don't have to explicitly draw the causal graph, but we are thinking in terms of causal graph and saying for colliders.
Jamie has something to say.
So I think you don't know that's the answer to your question, but it's very likely it's going to make a huge difference at some point in the sense, having the scale. 20 years ago, no one would ever have believed that machine learning was going to do what it's done. We thought, okay, it's a fancier kind of regression. We didn't think it was going to change the entire, world. It's hard to make predictions, especially about the future. And I think, if you think what's going on in machine learning now, even though, Pearl was saying anyone in machine learning who doesn't work on causality in 5 years will not be able to be hired anywhere. But even without that, what are they doing now? They're trying to find all the artifacts that, we can detect this, but it turns out because you're a male versus female, that wasn't what we were trying to go for. And they're getting much better at figuring out how to, replicate things in the data set and do things themselves to get rid of the artifacts, so that these patterns that clearly can be seen that us humans can't see, they are, I mean, just by that bit alone, moving in that direction. There are all these corrections they're making, so little ditsels aren't the key, are meaning it's more and more patterns are going to be causal if they find them in some sense. So what's the world going to look like? I have no idea, but I'll bet you we underestimate machines as we underestimated them before.
So that was an unexpected answer. Does anyone want to follow up on that?
One thing. So, I mean, Miguel gave an example where the expert could easily beat what would be the automated procedure, the cholesterol example. And so I just wanted to mention there is some room for scale in the other direction. And so one thing I've found sometimes in applied work is the interaction with the domain experts is sometimes not as fulfilling when it's kind of an open question. So if you get people who are very capable in the scientific domain, and you tell me how you decide, they sometimes just cannot list everything that goes on in their head. And so when we did it completely manually, I hope one day it will be completely automatic. But if you tell them, here's this massive automated summary of the published literature, be it observational studies or even basic science, and you just give them prompts, you can we did it manually by just extracting from prior studies things people adjusted for, and you were having a much richer discussion with a domain expert. So I suspect the machines, before they just completely replace us, they may make it a little easier to talk to each other across domains.
Yeah, I'm going to finish one thing I was saying about that I forgot to say, is the way we're talking here, everything is about, are you getting it right or wrong? It's verificational science. A lot of people don't think that's the big issue in science. It's some clever hypothesis about what you think is going on based on, your biological, whatever, your ability to think outside the box and so forth. And so if you think about hypothesis generation, I think there's a huge amount for these machines to do. I mean, there are these huge genetic networks, they just have to come up with some thing in the data they see over and over again, and then, scientists could say, I wonder why that is, and find it, but they would never even had the hypothesis had it not been for the machine, which may, if you ask what's science going to look like in 100 years, that may be 100 times more important than verificational science, because eventually they'll find out the keys to very deep things with these machines.
So I'm probably not the best way to answer this question because I'm old school. I really love tags, and I really love to ask the experts what they do, several experts, and I really love this type of conversation and go to the data and actually check that this is really what is happening. But yeah, definitely things are changing.
All right, so I want to wrap up the how do we know we're right question and then ask sort of a more open-ended philosophical question. So I just want to point out that Jamie's the only one who has answered the question. And he said no. How do we know we're right? We can't know. A lot of the questions a lot of the things that we've discussed have been about falsification of a model, that you can falsify the model that you've proposed. And I guess as someone who likes to analyze observational data, at what point, or is there no such point, when the plural of non-falsification becomes verification? So how many different ways do you have to falsify analysis before you feel comfortable that you actually are correct?
I think I can start. I mean, in terms of falsification, you mean like sensitivity analysis, additional analysis?
Falsify your DAG, all those sensitivity.
All the things. It is, I don't think there is, I don't think we can really quantify this. It has to be like, One thing that is important is like what aspects we are focusing. So what is it that we are trying to falsify? So I think it is helpful, again, to use the target trial structure, no? So like think of the key protocol of a clinical trial. And for each of these, try to say, okay, I use this eligibility criteria. What would have been instead if I use a slightly different definition? And that is because we use data that are extremely complex. So like in the clinical trial, you know you are going to enroll, let's say, a patient with hepatitis C. You know that the patient has hepatitis C when they are when they enter the trial. When you use big data like electronic health records, claims data, you don't know, so you will need to use like different definitions of what you mean. And that is for each aspect of the emulation that we are going to use. And so we should have, I think, the sensitivity analysis for each of these aspects, and there should be a key results of our studies, I think. I don't think there is a way to say, it's hard to say. I don't think there is a way that we can say, oh, the discrepancy here is too big. That makes me think that I had it wrong. But at least, we are honest. We present all our results or our finding under different assumptions, and it is there. And then it is up to the expert then to make their considerations.
I think that the answer is no, that we can definitely show, of course, but that's kind of feasible. I think it is.
It was your prompt, Miguel.
Right. I think that we can learn things. We can do things that we prove over and over that do not harm to the scientific quality of the study and might happen in many cases. We can also do research to learn which type of questions cannot be answered with observational data. And we have done that too. It's really hard to do that type of research. As Amy said, you're not going to get to attain by doing that. But when we find something that doesn't work in observational data, it is impossible. There's no way you can estimate the right causal effect using that type of data for that type of question. We send that to a journal. It's very hard to publish because the editors look at that and say, hey, you're sending us a paper that says that the results are wrong. Yes, they are wrong. They're very wrong. And we can show that they're wrong. And that's why we're sending it. Because we don't want people to waste their time trying to answer this type of question with these observational databases as best as possible. And the editors don't want to publish. So that is one of the challenges. We also have to show not only what works, but also in terms of the target trial data, but also what the limits are with some data sources. And once we have that, once we have a better understanding of the things, what are the best things that we can do with data, and what are the limits of the answers that data can give us, then it's a matter of using that when we don't have a randomized trial. And if the causal question is not very urgent, we can take our time. But if the causal question is urgent, then by using those best practices for observational data, we will have better evidence that it will be enough. That's how I see it. I mean, think about the plasma example that Aaron was talking about. That was an example. You have to make a determination. Do you use it or not? People are dying. Do you use it or not? So if you use some quick and dirty observational data when you cannot do things like that, it might work. It's not hurting people. Let's use it. Fine. That's no big deal. If you think about tocilizumab, people are dying. Do you use it or not? You look at the observational data to the best that you know how to do. You don't find any alternative explanation to data telling you this works. This seems to work. It's compatible with the big benefit. There is no other alternative explanation that any expert can think of. Well, that is where the problem is. Now, are we sure that we're right? No, but should we use it because people are dying at the intensive care units? If the answer is no, we're not going to use it because this is observational data and we'll wait 6 months to 9 months until the randomized trials are in. That's a problem.
Yeah. Okay, so I actually think that we are just at time now. So one, I would like to thank everyone for coming to the first annual ever CAUSALab Symposium. I see Kathleen sweating over there if this is going to be annual. But I hope that you had one got exposure to all the exciting things going on in the CAUSALab, and that you're as excited about the future prospects of causal inference as all the rest of us are. So thanks everyone for coming, and join us out in the lobby for refreshments, courtyard.
Causal count, or wait, I would say causal, the Country Community Gardens.
Okay.
But I realize it's very cold. We have to serve food out there, but feel free to come back to the Christie Cafe to sit and enjoy if you'd like.
All right, thanks everyone.